Respected Sir, Madam, my name is Aparna. I am pursuing my bachelor's degree in Electronics and Communication Engineering at Annamacharya Institute of Technology and Sciences, Rajanpet. Thank you to the organizers and sponsors for providing an opportunity for presenting our paper at this conference. Now, I am going to present a paper titled A Novel Multimodal Anatomical Medical Image Vision using Structure Extraction. My team members are Afrin, Abhinav Kumar, Kavita. We have done this work under the guidance of Mr. G. Obaleshu, MTech Assistant Professor, Department of Electronics and Communication Engineering. The contents on my project are Introduction, Objective, Importance, Methodology, Existing Method, Proposed Method, Implementation or Results, Conclusion. Introduction. Nowadays, medical modalities such as computer tomography, magnetic resonance imaging, positron emission tomography, and so on have provided clinicians with information of the human body's structural characteristics, soft tissues, and so on different perspectives. This provides a single medical images with limited information that may not be sufficient for making a critical decisions. Therefore, providing detailed information from a different perspective may help in making a better decision. So, we present a novel weighted term multimodality anatomical medical image fusion method. Objective. The main objective of image fusion for multimodal medical images is to retrieve valuable information by combining multiple images obtained from various sources into a single image suitable for better diagnosis. Importance. The image fusion process is defined as gathering all the important informations from multiple images and combines into a fewer images, usually a single image. This single image is more informative and it consists of all the necessary information. Image fusion is need not only to reduce the amount of data but also to construct images that are more appropriate and understandable for the human and machine perspective. Methodology. Existing methods. In the field of medical images, imaging techniques such as computer tomography, magnetic resonance imaging, positron emission tomography, and single photon emission computer tomography. Computer tomography helps to know the hard tissue information such as cancer, blood clots, etc. Magnetic resonance imaging helps to know soft tissue information such as central nervous system, abnormalities, and so on. Positron emission tomography images gives information related to various cancers, brain disorders, and so on. Single photon emission computed tomography helps in the diagnosis of infection, strokes, etc. These medical images require less memory and computational power as compared with maintaining their conventional hard copies. For storing multiple images for the same patient requires more storage, computational power and processing time. So, we are going for the image fusion technique. It plays a vital role in this regard by combining important details from different medical images into a single. In this method, we first import input source image to image enhancement. Image enhancement refers to the process of highlighting certain information of an image as well as removing any unnecessary information according to specific needs. Weights extraction. Image extraction. It is used to extract the crucial information from the source images The local contrast and silent stretches are estimated using the dense scale invariant feature transform descriptor and gradient magnitude. Weight map calculation and refinement. The weights related to structure and local contrast are merged in a way that both types of information remain intact. So, keep this information intact for each source image. We combine the weights, namely local contrast and silent structures. The weight map obtained contains noise and inconsistency that may cause artifacts. So, the weight maps are enhanced by using guided filters before performing the actual fission process. Pyramid decomposition. In this, the source images are fused to make a more detailed and enhanced image. Therefore, the source images and their corresponding weights are decomposed into different layers using the Laplacian pyramid and Gaussian techniques. The resultant layers of the source images are fused after multiplying with the associated weights, and we get the fused output image. Flow chart. As shown in the flow chart, first we import the input source images. Then, if there is any distortions that are eliminated by using image enhancement and converts RGB to gray. Silent invariant feature transform calculations. Here, silent invariant feature transform extracts key points from an image with certain local and distinctive features. This shift variant feature transform estimates the activity level and calculates which is more perfect and noise resistance. Local contrast and silent structures contain subtle and prominent details, and these are combined and calculated. Guided filter refinement used to remove the discontinuities from the final weight map, and this is given to the pyramid decomposition. Pyramid decomposition fuses the refined weight map with the source images, and we get the final fused output image is reconstructed. Implementation results. Tools used are MATLAB R2017B. Installed in PC. MATLAB is an allied electric for specialized registering. The image fusion framework is validated on 9 sets of CT-MRI and SPE-CT-MRI images of different diseases. It is compared with state-of-art image fusion methods, both qualitatively and quantitatively. Three pairs of PT and MRI images, three pairs of MRT1 weighted and MRT2 weighted images, three pairs of MRGAD and T1 weighted images. As shown on image 1, the first one is CT image. It shows the hard tissue organs, bones, so on. And the inputs second image is MRI scanning. It shows information about the soft tissues. It can be observed from findings that fused image method successfully preserved most details of both the source images. In image 2, the first input source image is MRT1 and the second input source image is MRT2. This shows the soft tissue or brain information. In MRT1, color silency feature fluid appears dark and gray matter is darker than white. While in MRT2 image, the color silency feature fluid is enhanced, therefore appears bright. As shown in the output, the fused image well preserved the gray and white matter and produces a good visual image. In image 3, the first input source is MR-GAD and the second one is MR-T1. These images are reflecting surface of the brain divided into left and right cerebral hemispheres. Here visual distortions are created in the fused image by the NSST approach. By this approach, we did not effectively preserve the gooey and silky information. The output fused image preserves the more gooey and silky information and contrast compared to the state of art methods. Conclusion. A new medical image fusion using new weighted term image fusion rule that works with less computational power. This method is suited for grayscale medical imaging and could be effectively used for the diagnosis of the patients. If the framework is implemented on a machine capable of capturing multimodal images of the same organ at the same time. Thank you to the organizers and sponsors for providing an opportunity for presenting our paper at this conference.